Welcome to Chapter 4, Part 5. In this video, we're going to talk about cycloalkanes and something called ring strain. Ring strain is a combination of angle strain and torsional strain. So we spoke about torsional strain in the last video, right? Torsional strain happens when you get that suboptimal dihedral angle between bonds on adjacent carbons. Angle strain happens when you make a ring and you have all of these sp3 hybridized carbons that want to be in a tetrahedral geometry. Now, if you remember from Gen Chem and your Vesper theory, a tetrahedral geometry is ideal when you have 4 single bonds around an atom because it allows them to spread out as much as possible and you get 109.5 degree bond angles. When you make a ring, you can't maintain those 109.5 degree bond angles because of the inability to rotate and spread out and also maintain that ring shape. And depending on the size of the ring, you have you get more or less close to that 109.5. So we can see a lot of angle strain in cyclopropane at 60 degrees, in cyclobutane at 90. We see something interesting with pentane. We're getting pretty close. And then we get further away as we get 6, 7, and 8 membered rings. And so we're going to talk about the conformations that different cycloalkanes can adopt, right? Remember, a conformer or conformation isn't the same as an isomer. Conformations are the same molecule, but just positioned differently. Build yourself a molecule. Twist the atoms around, right? As long as you don't break any bonds, you're not making a different molecule. You're just twisting it into a different shape, into a different conformation. When we look at the combustion data for cycloalkanes, we see something really interesting. Now, remember, propane has 60 degree bond angles, very far away from 109.5, and it's no surprise with all that angle strain, these are going to have the most energy. They're the least stable, right? And you don't see many 3-membered rings in nature for this reason. They're not particularly stable. When we get to cyclobutane and its 90 degree bond angles, it's better for sure, right? Significantly lower energy, but it's still, compared to everything else, high, right? So 4-membered rings, better than 3-membered rings, but still pretty stressed, a large amount of ring strain. Not surprisingly, when we get to that 108 degree cyclopentane, that bump in energy goes way down, right? The ring strain is greatly reduced in large part because of that angle strain reduction. But something surprising, right? Our 6-membered ring, 120 degrees is getting further away from 109.5. So you might expect it to go up. But in this case, it actually goes down. That 6-membered ring is really interesting. There is a reason why. My mother used to tell people I make hexagons for a living. My mom's not a chemist. But she would see my notes, and you're going to see by the end of this year, we draw 6-membered rings a lot. 5 and 6-membered rings are the most commonly occurring ring sizes in nature. We see them a lot in industry and pharmaceuticals. And this is why, right? That 6-membered ring has the ability to completely eliminate ring strain through one of its conformers. And that's what we're going to talk about today. So when we think about conformational analysis, right? So we're looking at conformations. We're going to start with the 3 and 4-membered rings. These are our highest energy guys. So we know the angle strain is bad on cyclopropane, right? We look at it, we got a 60 degree bond angle. But what about torsional strain? The torsional strain, if you build yourself a little 3-membered molecule, it lays fairly flat. There's not flexibility. In fact, if you try to build it with a model kit, some model kits will pop right open. You can feel the angle strain in the model. And when you look down one of these bonds, you are going to see that everything is fully eclipsed, right? The hydrogens will be fully eclipsed. I'm going to put the hydrogens over here. And then, let's see. They're both attached, as it turns out, to this one carbon back here. This is the same CH2. And so it is perfectly eclipsed. So you get torsional, like maximum torsional strain from the eclipsed conformation. The biggest angle strain you're going to have in a ring with that 60-degree bond angle. And so cyclopropanes, as a result, are not very stable, high energy. The cyclobutane is interesting, and now you got a little bit more flexibility, right? So for cyclopropane, it lays pretty flat, right? So max torsional strain, large angle strain. But something that can happen as your rings get bigger, they get more flexible. Again, you have a model kit or you want to play with the one in the lab, this would be a great week to do that. We'll build some of those rings and you can actually feel they're a little bit more flexible. So what happens, instead of a flat square, you get a little bend, right? They call it the puckered conformation. It does make the angle strain a little bit worse, but it relieves some of the torsional strain, right? It's not fully staggered, but it is less, well, not less, let's say. The torsional angle is going to be greater than 0, right? So it's not eclipsed, it's not perfectly staggered, it's not 60, but it's somewhere in between. So you get just a tiny bit more angle strain, but you relieve some torsional strain, and that makes it a little bit more stable, a little bit lower in energy, again, as we see here. Something interesting when we get, so the triangle, the cyclopropane is flat. The cyclobutane has the ability to pucker, right? So we're just gonna make it slightly folded inwards a little bit. When we get to 5-membered rings, right, that angle strain is greatly reduced, right? Almost to nothing, largely reduced. We do increase it a little bit, so these bond angles are going to be just a little bit smaller than 108, but we get something called a envelope conformation, right? So instead of saying it's puckered, we like to give all these conformers different names, right? And what happens is, as that molecule, right, it has kinetic energy, can't spin around those single bonds because they're locked in place by the ring, but you can create these little folds in the ring so that it's not perfectly flat. And so you kind of see this little carbon folding upward like the flap of an envelope. And as this molecule kind of bounces around in solution, this one will fold up and then come back down. This one will fold up and come back down. And so you're reducing that torsional strain on each bond a little bit as it rotates through the different conformers. So the average is a much lower ring strain, right? It's a lower energy. It's more stable, right? So the envelope conformation helps reduce the torsional strain. So it's not surprising that we see 5-membered rings a lot in nature, industry, pharmaceuticals, right, throughout this year together. It is the 5 and 6-membered rings are the most favored ring sizes. So we spend most of our time talking about that 6-membered ring because almost no ring strain is observed for a cyclohexane ring, which is interesting because this says 120 degrees. That is farther away from 109.5. So in theory, right, it would compress these other angles and it should be less stable. However, we know as we add carbons, we can start to fold and pucker or envelope, whatever. We can start to make this not a flat hexagon. So we can completely eliminate angle strain and torsional strain in one of the conformations. Look at this conformational analysis. What we call the chair is what we're going to focus on. In the chair conformation, and we're going to talk about how to draw it, but I'm going to draw one really quickly here. In the chair conformation, right? So it's a 6-membered ring. We call it a chair because we kind of like think about it as a headrest where you put your footrest, right? So it's a little reclining seat. When we think about this, we get 109.5 degree bond angles. Perfect. No angle strain. When we look down the bonds, if you look down the bond that's indicated here, it is completely staggered. So 60 degrees for your dihedral angles. No torsional strain. So that's why you kind of get this surprising dip where the 6-membered ring is lower than anything. Now, multiples of 6, you start for the same reason. You'll see 12 down here. 12-membered rings, getting that large is just not as common for other reasons. So we really focus on that 6-membered ring. That 6-membered ring, why is it so stable? 109.5 degree bond angle, so no angle strain in that conformation. Staggered, no torsional strain in that conformation. So, let me go back here. There are 2 chair conformations, and we're going to talk about that. But essentially what happens is your chair flip. It's called a flip, but it's not actually flipping over. What's happening is the headrest comes down and the footrest goes up, right? And so, again, the headrest is now the footrest. And so what happens is you bring down your head, the way they drew it is they bring up the footrest and you get a half chair. That's pretty high in energy because this part, I don't know if you can kind of tell what's highlighted there, is flat. So you reintroduce angle and torsional strain. So that's the highest energy conformer. You twist it up and to the twist boat and then twist boat. That is you're playing with the torsional and angle strain there. So they're somewhere in the middle. You go through your other half chair. You've brought your footrest all the way up. Now it's a headrest. Now again, flat here, so it's high energy. When you push that footrest down and make the other chair, drops right back into that low energy conformation that we see with the chair. When we look at a sample of a cyclohexane compound, why it's important to know this is to think about what it's going to look like most of the time. The great majority of your molecules at if you could freeze that moment in time, take a picture on the molecular level, the majority of your molecules will be in chair. Now, they're usually room temperature, common temperatures, common pressures. They have enough kinetic energy to flip around, flip back and forth. But because they are so much more stable in the chair conformation, that is how most of them will look. Now, here they're just talking about how there's no angle strain, no torsional strain, as we discussed. This is the Newman projection version, right? You can see carbon 1, 2, 3, 4, 5, and 6. You can see that in the chair position, you get that perfect staggered 60-degree bond angles, dihedral angles. So no torsional, no steric. We are going to be interested in a couple of things here, right? Notice how some bonds go straight up and straight down. And other bonds, here we go, sorry, go at an angle down and then up and then down and then up, down and up. That's going to be important. And so for us to discuss this, we need to know how to draw it. On the next slide, Klein gives you how he draws a chair. I don't do it the same way, and so I'm going to show you first how I do it. It doesn't matter. There are tutorials on YouTube. You can just type in drawing chairs organic chemistry and you will find a plethora of other tutorials. This is just how I do it. So I take kind of the seat of the chair first and I angle it to one direction. It does not matter which direction because you're going to do both. So I make them parallel and I offset them a little bit. Then I just, where the direction they're pointing upwards to, all right, I place a dot down here for my footrest and I connect. With the side that's pointing down, I place my headrest carbon and I connect. Then when I want to do my flip, and I'm going to use equilibrium arrows, this is not resonance, right? This one molecule can flip back and forth. It's not turning it over. It's not turning it around. If this is carbon 1, 2, 3, 4, 5, 6, I just want headrest to become footrest, footrest to become headrest. So I angled my parallel lines up to the left. Now I'm going to angle them up to the right. I'm going to connect the down side to the headrest. I'm going to connect the side pointing up to the footrest. If carbon 1 was the footrest, it is now the headrest. If 2 was going clockwise, then 2 is still going clockwise. It does not matter how you number this, where you start. It matters that you are consistent, right? So 1, 2, 3, 4, 5, 6. 1 was the footrest, now it's the headrest. 4 was the headrest, now it is the footrest. As we start to add substituents of varying sizes, you will get questions about not only is the chair the most stable, but which chair is the most stable? So it is important that you can practice and that you can draw these chairs. Now, since our test is online this semester, you won't have to do it on paper for me. However, if you are a future student and we are taking paper tests, you'll definitely have to draw it for me. So you should practice. But from here, we're going to add to it. So it's important that you get comfortable drawing this. Now, mine aren't pretty. They don't look gorgeous, but I can clearly see the end that's pointing up, the end that's pointing down, and, the seat in the middle. This is Klein's version. He starts by drawing kind of the top V. You can do that. You can use my way. You can look something up online. I don't care how you get there, but you need to make sure you feel comfortable with it. All right, so it is important that you've got certain lines pointing up and certain lines pointing down because we are going to start adding in the other 2 bonds on the ring. So I'm going to just draw just in the middle, unhindered by anything. Here's one of my chair conformations. Now, I'm going to use red. You have a bond on every carbon that points straight up or straight down. It is parallel to if you could just draw like a bar right in the middle of this ring, going straight up and down on the paper, it's going to be parallel with that bar. So, how do you know when to go up or down? I pick one place to start. I know on the headrest, the parallel, vertical line is going to go up. On the footrest, it's going to go down. Start with one of those because then it's alternating. And so once you lay one down, it's easy to do the rest. So if I have up, and this position is called axial, right? It's parallel to that center axis. And then the carbon adjacent to it will be down axial. Up axial, down axial, up axial, down axial. All right, so they alternate up, down, up, down. So what is the other one doing? What is the fourth bond doing? Let's use green. If axial is up, equatorial will be down on that atom. So it is not going to go straight down, but it is going to go below sort of that equator line, right? That horizontal line that you could draw. It's going to go angled down away, right? And that's equatorial. Now, if you have down equatorial, then next to it's going to be up equatorial. Down equatorial, up equatorial, down equatorial, up equatorial. All right? So, again, as long as you can get one laid down, you can get the rest because they alternate. Every single atom on the ring has an up and a down, an axial and an equatorial. And the axial and equatorials alternate, whether they are up or down. It's like what side of the ring they're on. Now, what is important, and this is just going through adding those lines, what's important is to understand how you can do a ring flip, how I can get from left to right. And so I want to go ahead and, okay, oh, here we go. I'm going to copy this. Okay, let's go to the next page. All right. I'll make this a little bit smaller. So what you want to do when you are doing a ring flip, what you need to know. The ring flip. Up stays up. Down stays down. What changes is axial and equatorial. Axial goes to equatorial. Equatorial goes axial. So if I redraw my ring, right, so I had my parallel lines going up to the right, so now I'm going to draw them up to the left. Headrest becomes footrest, footrest becomes headrest. Right, this carbon here is this carbon. So if my up axial, and I'll use red, if my red was up and axial on the left, it is going to be up and equatorial on the right. If it was down and axial on the second carbon, it's going to be down equatorial. Up equatorial, down equatorial, up equatorial, down. Oh no, I'm on the wrong, there we go. Down. All right, so all of those red bonds, the direction is the same. If it was up, it's up. If it was down, it's down. But it went from being parallel with that center line to being offset with sort of the equator of the molecule, going away from the molecule. So then my green bonds, which were equatorial, are going to go axial. So if on this highlighted carbon we had down equatorial, well, now that green is down axial. Up axial, down axial, up, down, up. Again, this is important because axial and equatorial positions are not created equally energetically. Right? So notice in their ring flip, whatever is attached is up axial, and in the ring flip, it is up equatorial. Okay? What is very important to know, and you write down, put it on a note card, chant it to yourself at night. The equatorial position is more stable, and it is because it is further away from the other things attached to the ring. There is a steric interaction, is it on the next slide? Yeah, that happens between axial positions that are on the same side of the ring. So this methyl group is closer to this hydrogen than this methyl group is to anything, right? There's the same methyl group, but in this conformation, right? In this conformation, that hydrogen's poking out over here somewhere. This is a steric interaction, and very specifically, it is called a 1,3 diaxial interaction. It's called 1,3 because that's the spacing, not necessarily the numbering for the name, but that's the spacing. In that axial position, you can see if you have that X, maybe that's that methyl group, that bigger substituent, it's going to get a lot closer to these other up axial positions. So the 1,3 and the 5 position. All right, you do not have that in equatorial. It's not necessarily gauche versus anti, although that comes into play depending on how many groups you have. It is a steric strain that happens just from being closer together in axial versus equatorial. So when you have, for instance, a methyl group here, not only does it prefer to be in the chair conformation, 95% of your molecules at any given moment are going to be in the more stable equatorial chair position, right? So that gives us a lot of information about the geometry, the 3D reality of the molecules we're studying. And as each substituent gets bigger, that effect only increases. So take a look at this chart here. Chlorine is going to give if all you have is chlorine, so a chlorocyclohexane, 70% of those molecules will prefer for the chlorine to be in the axial position. An OH is bigger than a chlorine just because you have that extra bond, not because oxygen's bigger than chlorine. Now you're getting an 83% preference for the alcohol to be in the equatorial position. Methyl, we already saw 95% prefers to be with the methyl in the equatorial position. You get to a tert-butyl group, that's 99.99% of your molecules are going to have that T-butyl group in the equatorial position. This is important if you have multiple substituents and you have to decide stability. All right? So, for instance, when we are drawing our rings, in this case, we are given a flat representation and wedges and dashes. And that is going to be how you were asked problems sometimes. And what you want to recognize is that we're talking about sides of the ring. Wedges and dashes are the same difference as up and down. So if you just always choose wedges are up, dashes are down, it doesn't have to be that way. You could flip it the other way, but you have to know that one is up, one is down, and be consistent. What that is going to let you know, can they both be equatorial or is one equatorial and I have to make a size distinction? Well, they've drawn the chairs here for us. We'll do some practice, but let's utilize this one. Notice the chlorine is up axial while the methyl is down axial, which makes sense. They're next to each other. One is going up, one is going down, and we know axial alternates. When we do the chair flip, chlorine is still up, but now it's equatorial. Methyl is still down, but now it's equatorial. So which one is more stable? Well, it puts those big groups in the equatorial position. So it's more stable and lower energy. You can't, what's the word I'm looking for? You can't overgeneralize though, because remember the relationship is every other. So sometimes up and down can both be equatorial. Sometimes an up and a down can be equatorial. We'll look at some examples. So for instance, now we went from a 1-2 substitution pattern to 1-3. So let's go ahead and draw this one together. So I just like to lay down both of my chairs. Definitely pause to take a minute to practice that. I like to just put one of these substituents on carbon 1. This has nothing to do with the naming. This is just for note keeping. All right, so on carbon 1, I have an ethyl group going up. I know on the headrest, up will be axial. So I'm just going to put ET for ethyl group. If that one is going up, well then I'm just going to make little hash marks. I know it's going to be down axial, up axial on carbon 3. But my methyl group is going down, right? It's going away. It's on the other side of the room. So down is actually going to be equatorial, right? These are just little hydrogens that I'm just marking out their location. When I do the ring flip, the ethyl was up axial. Now it's going to be up equatorial. The methyl group was down equatorial. Now it's going to be down axial. So which one is more stable? Well, okay, in each one, there is a group going axial, there's a group going equatorial. Which one's going to make the bigger energy difference? Methyl has 1 carbon, ethyl has 2. Right? So the more stable puts the biggest group in the equatorial position. So the most stable has the largest substituents in the equatorial position. When you are doing practice problems or quiz problems or test problems with this, draw yours, because it may be multiple choice, but it might be shifted around and you have to compare, right? You need to make sure that you are looking at an answer that matches this, that ethyl and methyl are on opposite sides of the ring because they are presented with a wedge and a dash. And then once you feel comfortable that you see the right representation, then you can think about the stability. Right? So they showed both. Because notice, I started with my headrest here in the upper right. However, they started with their headrest in the upper left. And so it looks a little different than what I drew, but it is actually the same representation, right? Up axial ethyl group, down equatorial methyl group. Up equatorial ethyl, down axial methyl. Ethyl group bigger, ethyl group bigger. Ethyl group is bigger, and so it is going to be more stable to get it in that equatorial position. Let's do one more practice problem. We'll talk about cis-trans stereoisomerism in a very short part 6. All right, so let's say we are doing, and I'm going to make this up on the fly, which is always tricky. Let's put a methyl group going up. Let's put a T-butyl group going up. And let's put an ethyl group going up. Right, I'm just going to do all wedges. So I'm going to go ahead and draw 2 chairs. I'm going to lay those down quickly here. I'm going to number this just to, please realize, I'm going to say this repeatedly. I am not numbering for naming. I am numbering for note keeping. So 1, 2. You want to make sure you're going clockwise or counterclockwise, but that you're consistent. 1, 2, 3, 4, 5, 6. That methyl group is going up, and so it's axial on carbon 1. Axial is down on carbon 2, but it is up on carbon 3. So that's my T-butyl group. On carbon 4, it'll actually be the ethyl group going up equatorial. Right? So we have axial, axial, equatorial. When we do the ring flip, up axial becomes up equatorial. Up axial becomes up equatorial, right? That it's important that you show that T-butyl group going up, but not straight up to indicate equatorial. And then on carbon 4, the ethyl group, which was up equatorial, is now up axial. So in both scenarios, we have a group that's equatorial. But in this one, 2 groups are equatorial, and most importantly, the biggest group is equatorial. So this one would be more stable. I have some practice up on eCampus working with, no, I don't. I will put a link up on eCampus for you with lots of chair practice. the practice exam has a few questions. Your quiz this week will have one of these on it. I highly recommend you doing some practice with this. Again, part 6 will be quite short.